All right, so welcome to this talk on multilingual search in Solr. So my name is Dave Troiano. I'm a software engineer at Basis Technology. We're a company that delivers both text analytics tools as well as digital forensics tools. And I'm on the text analytics side, really sort of in the service layer and the application layer that consumes the core NLP stuff. So I was actually really excited, like looking at the talks before me. I didn't know, if people would know what NLP is or things like that. And actually, both talks talked about NLP. Both talks talked about multilingual also. Stemming came up in both talks, so I was psyched to hear that. I'll define stemming again for everyone. So, all right. So overview of the talk. The first thing I'll do is really just define the problem that we're trying to solve. So, for some of you, you may see the title and not have any idea what I mean by multilingual search. You may not even know what Solr means. So we'll define those things. We'll go into detail, certainly more detail than the last couple talks about natural language processing. Natural language processing is really, it's crucial to search in general, even in the monolingual case. But especially in the multilingual case, it becomes even more important. Okay, and then finally we'll talk about approaches to multilingual search in Solr. So can I get a quick show of hands for who knows what Solr is or maybe has used it? All right, a lot of people. Okay. Developers mostly, or if you're a developer? Okay. All right, cool, good. So I probably won't, I won't do too much intro on Solr then, that's good. But I'll talk about approaches. So if you're familiar with Solr, you've probably come across this case where you ask a question, you ask someone, how do I do this in Solr? And the answer is always, it depends. There are like a whole suite of problems where there are multiple approaches and there's trade-off space that you have to navigate, and multilingual search is definitely one of those cases. So we'll talk about the approaches to multilingual search that you can implement in one particular search framework, Solr. Okay, so let me just start with an example of multilingual search, just to show you what we're talking about here. So this is a Google search that I issued a few days ago, and I entered a search query, Serie A. For soccer fans, Serie A is the Italian pro football league, soccer. And you can see that on, I had to page through a little bit to get some multilingual results, so I had to go to page 3 because Google, of course, is right in thinking based on the page I went to and my browser that I probably prefer English results. But if I go a little bit deep enough, you could see the second result here is actually an Italian news web page. And Google has also offered to translate the page for me because, again, it knows I'm English speaking. But here's an example where, mixed in with your English documents, you have an Italian document showing up. So that's an example of multilingual search. And our goal here today is to talk about how you build a search engine to do this. So we're going to build Google today. So strap on your seatbelt. So we want to build a search engine where your document corpus spans multiple languages. So that's a constant throughout. If your document corpus is monolingual, you have nothing to worry about. You're in the monolingual search engine case, and this doesn't apply. But your document corpus always spans multiple languages, and even within a document, you may have multiple languages. So an example of that might be, an email that's mostly English, and someone pastes in a little snippet in Spanish or something like that. So additionally, your queries may be within a language. So you may have monolingual queries, but a multilingual search engine, or your queries may span multiple languages. An example where they might span is, say, you're building a new search engine, and you know that your user is bilingual. Let's say that they say, I speak Spanish as well as English. A query for Obama, you might want to return both. You might want to interpret that query as both, Spanish as well as English, and return results for both. So Google, of course, is all of the above. The web is obviously a multi-billion document corpus that spans multiple languages. And Google is very good in terms of having one search box that, if I put in a string of German, it'll be very good in returning me German documents. Okay, so you guys are going to get very tired of this graphic. I'm going to keep going back to it. And I have multiple versions of this graphic, but this is basically, the basic data structure behind a search engine. At the bottom here is an inverted index. So how do you build, a fast search engine? The basic data structure is always a mapping from terms or words or tokens to the documents that contain that thing. So here if we think about how a search engine processes a query, in this case, Clinton speaking, the first thing that happens, sort of the entrance into the search engine is an NLP pipeline. So NLP is natural language processing. I'm just going to say NLP from now on. So the first step is this NLP pipeline that takes text, whatever it is, raw, unstructured text. You might not know what language it's in. And it produces what I'm going to call terms or words. So here, this query, Clinton speaking, might go through an NLP pipeline and produce terms, Clinton and speak. Okay, and let's say that so second arrow here is what do you then do with those terms? You want to do a read against your index, and let's say you wanted to find documents that contain both Clinton and speak, and you can do a simple lookup of each term, find your list of document IDs, and take the intersection of those. So on the other side is, of course, indexing. So how do you get this data structure at the bottom of everything? And it really looks the same. So the only difference is that rather than a query at the top, you have your document. And rather than reading from your index, you're writing to it. So this is just the indexing side of it. Here I have this example of, in the previous slide, I have this document ID 123. So here's document ID document 123. Bill Clinton spoke about, et cetera. Maybe this is a news article. That gets fed through an NLP pipeline, often the same exact pipeline. If you're familiar with Solr, this pipeline is called an analysis chain. You tie it to a field type. And you often use the same exact pipeline at query time and index time. So in this case, we'll produce, Bill Clinton speak about. You can see that there are a few things happening here. There's some simple things like lowercasing. And then there's some more complicated things like how does spoke become speak? So that's one piece of the NLP pipeline. And so this is the other side. This is here's our whole picture of everything. Your queries on the left that are reading, that end up reading from your index. And on the right, you write. Are there any questions so far? No? Good. All right. So as in the previous two talks, definitely feel free to pipe in with questions, comments. OK, so Solr is part of the title of my talk. So where does Solr come in all of this? So this is an abstract picture of what a search engine looks like. Solr is the framework that we're going to talk about today that really does everything from your query, everything, you take your queries and your documents, it does everything. So include, your NLP pipeline is specified within Solr, and then obviously all the way down to your storage layer is all handled by the framework. Okay, so let's talk more about this NLP pipeline and what happens within it, and then and also why it's so important in the multilingual case. So there are a few sub-processes that happen within an NLP pipeline, and you can think of these as generally building as you go. So for the most part, the first thing you need to do is detect the language that a piece of text is in. Often you don't even know. Sometimes you might, and this might be an optional step, but this is really step one because the rest of the steps all have their own algorithms and rules depending on the language that it's in. So step two is tokenization, and then which is breaking text into words. And then there's some a little bit more complicated NLP steps that happen afterwards: decompounding and normalization. I'll leave those undefined for now because we'll talk about them. So language detection. So I mentioned this is often required in indexing. It's not always required. So you can imagine, if you wanted to build a search engine for users to search Wikipedia. I'm not sure why you would want to do that because Wikipedia has pretty good search, but let's say you wanted to do that. You could hit Wikipedia. Wikipedia has an API. But the thing about Wikipedia's API is that it's actually per language. So you can query Wikipedia and say, give me everything in en.wikipedia.org, and then in jp.wikipedia.org, et cetera. And so right there, you know the language up front. It's given to you. So language detection wouldn't apply there. Did you have a question before? Oh, OK. Language detection is typically not used at query time. It could be, and I think there's some interesting work to do here. And there are a bunch of reasons why it's typically not. First off is that language detection really is, you get higher confidence language detection the more text you have. And because queries are generally, very short, you tend to have lower accuracy. Even worse than that, sometimes you don't even know. So the string Obama, for example, named entities is the classic case. So Obama, O-B-A-M-A, will appear in that form in English documents, in German documents, Spanish documents, et cetera. So given this query string Obama, or other named entities, iPhone, for example, for product, sometimes it's totally ambiguous, so even to people, so you can't expect the machine to know what to do. Third is that the end user applications often know the query language, so based on browser settings, for example, or even based on different endpoints. So the Wikipedia example is, or the website, there's the English Wikipedia that has a separate website, and if you're on English Wikipedia, Wikipedia can probably assume that your query is going to be in English and that you care about getting English results because that's the only option. The final reason here is that there's not really a readily available pattern, at least in Solr, to do language detection at query time. There is at index time, but not really at query time out of the box. Okay, tokenization. So I mentioned this, it's breaking text into words. If you only speak English or English and other European languages, you probably don't think of tokenization as a difficult problem for a machine to solve because we're blessed with white space between words. So you can write a pretty, anyone who's taken Computer Science 1 can write a pretty decent English tokenizer. That's not the case in all languages. So in Chinese, Japanese, Korean, there are no spaces, unfortunately. So in Chinese and Japanese, I'm pretty sure there's no spaces at all. In Korean, I think the spaces are between sentences. But that really doesn't hurt, really doesn't help. If you think back to, we need to take text and get terms, sentence boundary doesn't help at all. Okay, decompounding. So this is breaking compound words into subcomponents. So there are a bunch of languages that There are some compound words in English, but they're more common in other languages like German, Dutch, Korean are the prominent examples that come up. So Samstagmorgen, maybe I'm pronouncing that right, means Saturday morning in German. So German, in German, compounding is very frequent. And the reason why this is important in search is that you might have a document that contains a compound word, and you'll want to, for recall, you'll want to index the compound word probably, as well as the decompounded parts, so that if there's an article that mentions Saturday and morning, but not in the compound form, a query with the compound word will return that document. So, okay, normalization. So this is like the umbrella term where stemming is an example. So do people remember stemming? I think it was, I won't go over stemming again because it was mentioned in the last couple. But the idea of normalization is to reduce word form variations down to some canonical representation. So verb forms was the example mentioned in the previous talk. It's a great example. And also, let's take the speak example. So speaks, speak, speaking, spoke, maybe even speaker might all collapse down to the canonical form speak. And this is important for a couple reasons. One is, so recall, which is precision and recall are, well, what are the terms that Tanya used? They were different. I'm used to precision and recall in the search space. They're equivalent to sensitivity and specificity, okay? So critical for recall in that you want queries of any form of a word to find documents with any form of a word. So again, if you think back to Tanya's talk and the code that she showed where she was searching for, issuing more like a database query for switching, switch, switched, switches, et cetera, doing that all out by hand. In the search case, you don't want to do that for a couple reasons. One is that it's error prone. What if you miss different word forms? And then two is also performance. So if you can do this, this collapsing down to a canonical representation before you get to your underlying data structure, it's less space, it's more performant. So there are two approaches to this, stemming and lemmonization. So stemming, we've heard about, it's basically it's a rules-based approach. I just say it means, chop off the end. That's generally what it means, generally what you're doing, according to some rules. So arsenal and arsenic, AL and IC in English are often tacked onto the end of words. So those would both be stemmed to arson in one particular stemmer. Did you have a question? No, okay. Lemonization, so this is less to do with strings and more to do with mapping words to dictionary forms of the word. So spoke to speak is a good example of this. Spoke will not lematize to speak. Or sorry, spoke will not stem to speak, but spoke will lematize to speak. So generally, you get both higher precision and higher recall with lemmonization. Okay. I think I'm going to skip over the Solr intro. Everyone, or most people here have used it. Wildly popular search server framework built on Lucene. It's open source. If I had a scroll of the major companies that use Solr in some capacity, it would be one of those scenes where I drop it and it just hits the refrigerator over there. A couple that I know of, at least at one point in time, eBay was using it in a couple ways, Instagram, Netflix, the list goes on. So are there any questions so far? Yes, thank you.
So Bill Clinton spoke. How do we take the spoke and also include words like talk is a very
Right.
different
Right.
word origin than spoke.
Right,
Or
right.
do you even do that?
Okay. So the question was, how do you take a word? So in the example, Bill Clinton spoke. How do you also treat spoke the same way as talk, for example? So a query for Bill Clinton speaking. If you want to find find Bill Clinton talking. So you wouldn't do that with lemonization or stemming. Those are really per string, per word form. There are synonym filters in Solr, so that's there for you where as part of your configuration you specify the words. You can basically specify a cluster of words that all mean the same thing, and that's one way of doing that. Yeah. Yes.
You say lemonization is a per word technique. How do you take spoke to speak instead of spoke to wheel spoke?
How do you take spoke to
Speak instead of like
Right.
a physical object.
Okay. Yeah. So context around it.
Okay.
Yeah. Yeah. Okay. So we know a bunch about NLP, and now let's talk about NLP within Solr. And what the concept within Solr is a field type. So Solr is document oriented. You have documents with fields in them, and there are types associated with those fields. Your NLP pipeline is really specified within your field type. Okay, so we'll talk about a few indexing and querying strategies in Solr for implementing multilingual search. So there are a couple. One is field per language. So you have a separate field for each language. So you might have a content underscore English, content underscore Spanish, etc. Core per language. So a core is basically an individual Solr index. So there's one particular schema tied to a core. So in this case, you would, rather than have field per language but all in the same core, you could have your English core, your Spanish core, et cetera. And then we'll talk about one other that's a little bit more bleeding edge approach to this. That's someone that we've worked with closely came up with. So how does this look in your Solr schema? Field per language. This is a very simple example where you just define two fields. So I define content Cjk and content ENG. And here's an example of the field type for text Cjk. And this is basically the vanilla Solr way of defining a field that is Chinese, Japanese, or Korean. So going back to this slide, I say max precision recall requires NLP pipeline per language, and then I just specified a pipeline that lumps a bunch of them together. So I think it's generally true, but you could probably say that you want an NLP pipeline per group of languages that are similar in some way. And we'll talk about Cjk. I'll give an example at the end of why they're treated similarly.
Configuration file for your
Yeah, so this would be like the field and field type specification part of the Solr config. Yeah. So at query time, you can query Solr in a bunch of ways. There are SDKs. Under the covers, though, it's a REST API. So here's an example of how you would query this, and I'll go through this piece by piece. So in the field language approach, let's say that you want to query across languages. The first interesting thing to note is this Q equals Serie space A, URL encoded space. So that's my query string. That's maybe what the user typed into their search box. Def type eDismax. So Dismax, who's familiar with Dismax or has used it? All right, no one. OK, so Dismax is a query parser that is included in Solr. And the key thing that it allows you to do is to query over multiple fields simultaneously. So one way of doing a query across languages is to do your own Boolean logic and say, let me find this term in content CJK and content ENG, et cetera. Dismax is a convenience layer for you. There are a bunch of other features of it. So as part of Dismax, one of the parameters is this QF query fields, where you just list out the query fields that you care about. So in the field per language approach, really Dismax is your friend. You could also do the Boolean logic thing. OK, core per language. So remember that this is an individual index dedicated to each language. So here, rather than your universal schema, you have a Cjk Core. And in this core, rather than calling our field content CJK, we might as well just call it content. And that'll help us out later, and I'll show you how that helps us out. But because there's only one language we care about, we'll just call this content. And the field type could even be text, because you're not going to have other language field types defined in that schema. Let's say we continue to call it text CJK, and it defines again this Cjk pipeline. So how's the query different? Your Q param is a little bit different. So rather than just a string and you don't talk about fields, we are going to specify the field here. So we're going to say find within the content field this string Serie A. And the difference here between the last approach and this is that whereas the last approach used Dismax and its capability of listing fields, here we're using a feature of Solr. Solr has this distributed search feature where you essentially can specify multiple search endpoints that you want to hit. And Solr will hit all of those and merge results for you. So that's the shards parameter where you would hit a shard, or an index called article CJK. That's your Cjk Core, and then also articles ENG. So those are that's the equivalent way. OK, so how do these approaches compare? So this is a very simple, comparing simplicity and speed. So field per language is by far the simpler approach to this. If you think about the core per language approach, you have a more difficult backend management because you have multiple cores to deal with. In the core per language approach, you have to worry about things like how common a language is in your corpus. So if English is very common, you may want a much more scaled backend infrastructure to deal with English, and then a tiny backend infrastructure to deal with an uncommon language in your corpus. Whereas in the field per language approach, it's all one logical index in terms of Solr, so you don't have to deal with those issues. So why would you use core per language then? It comes down to query speed. So generally, especially if you want to query across multiple languages, the core per language approach will be faster for you. And the reason for that is that all the heavy lifting is happening per language on different machines, potentially. So you can scale out your queries in the core per language approach and squeeze a little bit of performance out. Questions so far? No? OK, so now so this is the fun stuff. This is the bleeding edge that right now is, so one of our customers came up with this approach. As of now, it is available on his private GitHub. And it's also described in the most recent Solr in Action that came out, I think in April this year. And it is basically the simplest of all approaches in terms of how you specify it. So really, we're putting all content, regardless of language, in one field. And how do you do that? Well, really what the creator of this, Trey Granger, who sort of heads up search at CareerBuilder, Really what he came up with was sort of a new field type. I call it a meta field type that really just knows how to map a piece of input into the correct underlying concrete type. So there's not actually any NLP or anything. It's not much more than a map. It just shows you which concrete class to use. And it's currently a patch submitted to Solr. May become part of vanilla Solr soon. So here, going back to our picture, here is how this might work. So let's say that your users, you know that your users care about English and Spanish, and they query for Clinton. So what Trey came up with is basically a way to encode the languages that you care about in the field. So your query, you as the sort of the search backend developer might prepend that, okay, in square braces. You'll say, okay, I care about English and Spanish. Now, what happens at this first arrow here is the NLP pipeline, really. But the first thing that happens is that you inspect that. Okay, you say, okay, this is English and NES. So what I'm going to do is apply the English NLP pipeline to this text. At the same time, I'm going to apply the NLP pipeline, the Spanish NLP pipeline to just the query string Clinton, and I'm going to merge results, deduplicate tokens, et cetera. Okay. So simplicity, really awesome in this approach. There's a little bit of a subtlety that can go wrong if you do this, and for that we need to do a little bit of a tour into results ranking. So we talked about precision and recall as being important in high quality search. The thing that I didn't mention, and that you could argue is even more important, is results ranking. So it's not just good enough that you get back all the results that a user cares about, and that you don't get back crap results. So that's the precision recall. You care that the order of them is right, that you're bringing back relevant results. Google is a classic example of this. If Google had perfect precision recall but bad ranking, and the page that you cared about in your results was, on page 10, Google would not, you wouldn't even know what Google is today because they would fail. No one goes past the first page. Generally, you don't even go past your first page of results. So, yeah, question? Okay, time? Yeah. Let me go through one fun example here of how this can get thrown off in this alternative approach. So soy is this common word in Spanish that means I am. And you could say that it's relatively rare in English, soy, the bean. So I want you to consider what happens when you have a corpus of, say, English and Spanish food recipes, and put your vegan hat on and imagine that you're querying for soy dessert recipes. Okay. So generally, if you were issuing this query against only English, there's this concept of IDF, which means inverse doc frequency, which basically says that if a word is uncommon in my corpus, then a match against it is more meaningful in my results. So in this query, soy dessert recipe, let's say that because this is a recipe corpus, recipe is your most common term, and then desserts are a common kind of thing that you make a very general term. Say that's next frequent, and then soy is, that's less frequent, and then soy is your least frequent. That's an ingredient. So a query for soy dessert recipe should return documents that contain soy dessert before it returns documents for dessert that contain dessert recipe. So that's an example of IDF being important. Yes? Yeah. Yeah.
I mean, it won't be perfect, but
yeah. Yeah. So the question was, could you Could you do other things other than just the basic TF IDF scoring? Could you boost certain fields? Yeah, the answer, yeah, definitely. Back to the Dismax parser, there's actually a bunch of built-in functionality for doing that, where you could say, for example, title, a match on the title field should weigh very heavily, but a match on the the recipe content field shouldn't match as heavily. So back to this crazy example of being searching for soy dessert recipes. So you could imagine that since your corpus contains English and Spanish, and you put all this into one field, you have made soy a common term in your corpus. So those two documents that we were looking for, one contains just soy dessert, and the other one contains dessert recipe. Right? Your IDF is now thrown off because soy is common, so you may end up getting dessert recipes back when the ingredient is probably more important to you. So something to keep in mind here if you mix within a field. So I'll start wrapping up here because yeah, we're tight on time here. So how do you enhance your NLP pipeline? So everything up until now has been what's available in Solr out of the box, and I have to do a little bit of selling to you guys. So let's talk about how limited NLP in Solr out of the box is. So Cjk Tokenization, I'll go through an example of that. There is no lematizer in Solr out of the box, so you can only depend on stemming. And stemming can give you both poor precision, where let's say that query for arsenal will give you documents containing arsenic, as well as poor recall. So the spoke speak example, spoke does not spoke does not stem to speak, so you won't get a match there. And then decompounding, again, there's no decompounding functionality in basic Solr. So Rosette to the rescue. This is the product suite that my company offers. I'll go through just one example of Cjk tokenization. So this string of Japanese characters, something about Kennedy in Massachusetts, really just contains 4 words. So the Rosette platform, which is offered as a plugin to Solr, will properly tokenize this into the first 4 characters, then the next, and then the rest are all one word. Going back into why vanilla Solr chose to lump Cjk altogether, even though they have totally different rules for tokenizing, is that the tokenizing is sort of the simplest thing ever. Again, it's something that anyone could code up if you know a programming language, and that's just bigramming. So your first 2 characters become a token. Your next 2, so characters 1 and 2, 2 and 3, 3 and 4, and you shingle that way. And this obviously, this impacts performance, precision, and recall by taking this bigramming approach. So first off, you have to index a lot more stuff. Precision, so how does precision hurt here? Can anyone think? Scoring, yeah, right, so scoring. And then also, notice that there are single character words in Japanese. Your bigrams don't catch that. And then recall also. You were saying that every 2 character token here is a word, right? And if in this this phrase up at the top, 2 characters are over a word boundary, but there's actually another word where they appear next to each other, you've just hurt your precision. Sorry, that's precision. Okay. So how do you plug into Rosette and Solr? It's the same way as the vanilla approach. You just specify this different class and the language. And the Cjk languages are per language for us. And it has to be that way because we're doing analysis, morphological analysis per language to figure out where words break, for example. So language ZHO would be how you make a field type for Chinese. And to see more about that, so there's we have this product, Search Essentials, that is offers a plugin both in Solr as well as Elasticsearch for using our stuff. So quick wrap up, multilingual search is everywhere. You use it all, it's happening under the covers all the time in the products you use. We looked at Solr as a search platform and how to implement this stuff in particular in Solr and the trade-offs of the various approaches. And really the final point here is that your search quality is really only going to be as good as your NLP tools. So you need quality normalization, quality tokenization, et cetera, to build quality search. Everything starts at your NLP pipeline at query time and index time. That's it. Any questions? Yeah?
Do you guys do anything interesting with low resource languages?
Low what languages?
Low resource languages?
Do we do anything interesting with low resource languages? What's a low resource language?
Not English, Spanish, Chinese, something like a language where you don't have large Tagalog. And you don't have
Okay. Yeah, so depending on the product, like our language identification works with, I think, in the 50s numbers of languages. So, I don't know if, there are a lot more than 50 languages in the world. So I guess it depends what you mean by, by the smaller languages. Depending on the product, it's support for anywhere in the 20s to the 50s. Entity resolution is sort of our, everything's building up to entity resolution, which is how you map, here's an entity mentioned, George Bush. How do you map that to the right George Bush? That is newer for us and has less language coverage. That's a handful right now. That's a new product for us. Yeah. Yeah. Right. Right. Cool. Okay. Yeah. That's a good point. So the point here was that even in older languages in Latin, you have the same problem. So what I was talking about with CJK languages, as sort of the classic examples we go to, where you don't know how to break words, or it's difficult for a machine to break on words. The point was that there are other examples of that too. Any other questions? All right, cool. Well, thank you. I'll hang out over there if you want to come and talk to me by the coffee.